Hi. So what we have done up to now, we are dealing with sequential circuit synthesis. We have seen step by step how you can synthesize a sequential circuit. The next thing we have done was to give an example, which is serial adder synthesis. We have done it step by step in details. Now I am going to give you a synthesis, example synthesis, modulo8 synthesis. Now some of the things, the regular things to do, I'm going to leave it to you, and the mainframe or infrastructure of the synthesis I will try to explain to you. So in here we said the example that we are dealing with is modulo 8 counter. So we are looking at a box now. We don't know what is inside, but we are saying that there is one input. This is clock, and we've got three outputs: Y1, Y2, Y3. So for each clock pulse, we are going to count the output. So if your present state is 5, when the clock pulse comes, it's going to be 6. If your present state is 6, when the clock pulse comes, it becomes 7. So in this case, since we've got 3 state variables here, means the highest number that we are going to see is 7. So this counter counts from 0 to 7 and back to 0 again. So if I write it in all states here, so our counting is going to be 0, 1, 2, 3, 4, 5, 6, 7, then 0 again. So this is the box now we are going to design. On the other hand, we said input is just clock pulse. Normally, clock pulses is not considered as independent variable, so we've got to keep that in mind. And if you look at these outputs, the high number is 7. If you consider the 0 as well, the total number of different number that we are going to observe is 8, isn't it? That's why it is called modulo 8. So if you look at the output is present state is small 1, next state is capital 1, like that. So there is no any z function here, because you might call it z functions are these y1, small y1, small y2, small y3. In this case, this is a Moore machine is now. So if we've got 8 states, means 3 state variables, means 3 memory elements. So I determined at this stage we are going to use 3 memory elements in 3 flip-flop inside. I know that. What I don't know is the combination circuit. How you're going to do it? So look at this table now. You don't need to draw maybe state diagram here, but if you do so, let me do it. Yeah. So since the states here is 0 to 7, we're going to represent. So we can give the total number of state is going to be 8, isn't it? A, B, C, D, E, F, G, H. So let's say A, B, C, D, E, F, G, H. Now if you say if you give these letters to these states, you're going to give a code as well. So I am going to give the coding, I'm going to make the state assignment coding in the sequence, in the counting sequence. So that means 0, 1, 2, and 3, 4, 5, 6, and 7. Now we are going to count a clock, so it's going to be, when the clock comes, it's going to change the next state. That means it is going to count 0, 1, so each clock pulse comes, your present state increased by 1, isn't it? So that's the state diagram. If you transfer this state diagram to mathematical model, it becomes like that. If you look at this, you've got 3 state variables, so total number of state is 0, from 0 to 7. So when the clock pulse comes, right hand side is the next state functions clock comes. So if your flip-flops are positive edge sensitive, that means positive. When the pulse positive edge comes in, your present state 0 becomes next state 1. If it is 1, it becomes 0. So if your present state is 1, your next state 2. If your present state 2, your next state 3. If your present state is 3, then your next state is 4. Present state 4, next state 5. Present state 5, next state 6. Present state 6, next state 7. Present state 7, next state 0. So that's that order, isn't it? So from now, what we could do, if you know the present state and the next state, that means you can find the memory element input functions. Z function, as I said, is the same as y1, y2, y3. You don't have to rewrite it. So you're going to put, if you are going to use T memory elements, so it's going to be T1 to T2, T3, and use the inverse definition relation of T, you're going to get these 3 functions. From these 3 functions, you're going to draw the circuit. Now, the step that we are going to do here is the same steps that we followed while we are designing serial memory elements. So if you watch this video, serial other video, then you can learn the steps that we are going to apply here, right? Now, but I would like to explain something different here. When we said T-type memory element here, we already know that the memory elements, there are 4 of them, D, T, SR, and JK. How we are going to make the decision which memory element we are going to use? In here, we determined number of memory elements, but we didn't say anything about memory element type. So there are 4 types here. So the functions that we're going to find is the memory element input functions. So 3 memory elements means 3 memory elements. Then for D type, 3 functions we are going to design, isn't it? For each one of them, D1, D2, D3 is going to be D1, D2, D3. So similarly, T-type memory element used, so 3 function again. But when you come these 2, since this type of memory element has got 2 inputs, for each memory element, you need to find 2 functions. So total number of functions that you're going to design is going to be 6 here, 6 here. Function you're going to design, right? So you might say, okay, since we've got 6 functions to realize here, don't use SR and JK type memory element, use D and D type memory element. This is not true because these D-type and T-type memory elements, if you examine the inverse definition relation of these memory elements or excitation table of these memory elements, you're going to see no don't cares at all for D and T. No don't cares. So if you examine SR or JK type memory element, you're going to see that in excitation table there are don't cares. There are don't cares. So conclusion is this. In here, although you've got three functions to realize, which seems good, but there is no don't care. In here, although the number of functions that you're going to design is doubled, but in these functions we've got many don't cares in it. Many don't cares in it means the minimal function cost is going to, could be probably less than the other one. But we cannot say this always. Then, from the engineering point of view, while you are designing a sequential circuit, you've got to give four designs for each type memory elements by using different memory elements, that is. Then that means you're going to see the combinational circuit costs for those memory element inputs. So you can compare these costs and then you can make the decision that on paper you do that by hand. Then you can say that for this sequential circuit, such and such memory element combinational circuit is cost minimal. Then you can choose that memory element. So this is one of the conclusions that we can say at this stage. Now, when you come to the next modulo 8, this is another modulo 8, different, a bit different from the previous one. This is once again modulo 8 counter. So in the previous one we were counting the clock pulses. In here, since it is a sequential circuit, synchronous sequential circuit, there is a center clock. This clock is the same as the previous one. But what we are counting here is not the clock pulse, but pulses which come to the X input. So we are counting is X input pulses. Count X. So as soon as a pulse comes in, whatever your state is going to be next state increased by 1, that is. You might say that, okay, why do we need such modulo 8 types in practice? Yes, we do need. I can give you an example for this. When you are entering to university, you are passing through a barrier and you must show your identity card, and then you would be able to pass. So each person comes, it is counted inside. When it is counted, that means you can say that today such and such number of students or academic personnel came in, and how many of them went out. The difference is how many people are in the building. So this is one of the practical usage of a modulo 8 counter like that. So what's going to be, let's examine in terms of synthesis. Now the state diagram is like that. when x value is 0, you're not going to count. No count. x0, no count. No count. No, 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 no. Here, no. Here, no. X equal to 0. X equal to 0. No, no, no. But when x equal to 1, so that counts. What that means, if your present state is 0, next state becomes 1 when x equal to 1. When x equal to 1, your 1 becomes 2, 2 becomes 3, it goes like that. So this is the state diagram. If you transfer this state diagram to mathematical model, it becomes this. Now in here, we've got x0 and x1 values. This is an independent variable. And this s's, small y1, small y2, small y3, is the present state. So we've got 4 independent variables. In the previous one, it was just 3. There were no x input there. So in here, 4 independent variables. So how many next state functions we have? So these are the next state functions. Each column shows one next state function, y1, y2, capital Y1, capital Y2, capital Y3. So 3 dependent functions, right? So this table shows me x equals 0, no count. You see, you can see it here. If your present state 0, when the input is 0, no count, 0, 0. When the input is 1, your present state 1 becomes, your present state 0, sorry, becomes next state 1. Present state 1, your next state 2. So it goes down, present state 7, next state 0, when x equal to 1. So I consider it here, this counting. So this column here, counting column. If you see this first column, x equals to 0, no count, isn't it? So this column, no count. So once you've got such a state table like that, so you can transfer these functions. First, you've got to make the decision which memory element you're going to use. Assume that this memory element is T-type memory elements. So for T-type memory elements, you're going to have T1, T2, T3 functions that we're going to find. How are we going to find that? We've got 4 independent variables here. Then you're going to make a table. This table is going to be like that. X, Y1, Y2, Y3. And your next state is Y1, capital Y1, capital Y2, capital Y3. So 0, 0, 0, input 0, no count 0, 0. When it is 1, 0, 0, 0, it is 0, 0, 1, isn't it? Input is 1, present state 0, you do the counting 1. So how many rows like that? It's going to be 16. 4 variables, 2 to the power 4, 16. So you're going to fill up this by looking at this state table. Then what you're going to do is use the inverse definition relation of T-type memory element. That means this. So you're going to find now T1, T2, T3 functions in terms of these independent variables. Now right hand side, dependent, so this is double line. These dependent variables, these are independent variables. So I'm going to find that T1, T2, T3 functions in terms of these independent variables. How I'm going to find that? you're going to compare small y1 column with capital Y1 column here. So for first T-type memory element, your present state is 0, your next state is 0, 0 to 0 change here is T input must be 0, isn't it? So it's going to be 0 here. If we look at this one again, it's going to be the same, isn't it? Small y1 0, capital Y1 0, so it's going to be T1 0. So for Y2, you're going to compare different columns now. For Y2, you're going to consider this column as the present state for second T-type memory element. In here, this column is going to be your second memory element next state. So compare these two 0, 0, 0, 0, isn't it? Whether it is x is 0 or 1. So it is same as this, it's going to be. And the third one, let's use another color for that, blue, let's say. For the third memory element, this is the present state. And this is the next state. So T-type memory element input. When all these 0, present state 0, next state 0, so you are here and it's going to be 0 here. When you look at the second line here, you see in the previous one x was equal to 0, in this one x is equal to 1. And your present state, your present state is that 0, your next state is this 1. 0 to 1 change, 0 to 1 change is this. For this, your input must be 1, isn't it? That is inverse definition relation of T flip-flop or excitation table. So I'm going to put 1 here. So for 16 inputs here, you've got to find out these functions values. So I have done 2 of them. So you could do your own, the other 14 of them. So you're going to find these functions. So if you consider now this side and this side, so that means you have found memory element input functions in terms of these independent variables. So you can transfer all these functions to kernel map T1, T2, T3, and from this kernel map, the other empty cells here, that means the value is equal to 0. So you're going to find for each T1 function corresponding minimal function, this is the minimal function T1, this is the minimal function for T2, and this is the minimal functions for T3. So it should have been 3 actually. Right? So once you found these memory element inputs, that means you can do the design. So let's compare now this modulo 8 with the previous modulo 8. You see here, that is the previous modulo 8. You're counting the clock. This one is the new modulo 8, which counts that x. So if you compare those two now, one AND gate, one 2-input AND gate, 2-input AND gate is additional in terms of cost. So if you are counting the external x, then you're going to use one additional AND gate. In here you've got only one AND gate. So that's the two circuits to be compared. Okay. So another example, in order to see the differences, is this. You see, look at this counter. This is another counter. How it counts. Let's say it counts clock 0, 1, 2. It jumps to 4, 5, 6, jumps to 0. So you can design a counter like that. So if you design a counter like that, what you're going to say is this. At least you've got three memory elements, y1, y2, y3, because you've got 3 bits. So 3 memory elements. If you use 3 memory elements, that means you're going to have here 8 states, isn't it? 8 states. So in your diagram, you've got only 6. So which state is not seen here? 3 state 3, not seen. 4, 5, 6, 7 is not seen. So when you write these 8 states, so one of them is going to be 3, the other one is 7. That means you never come to these states because of that state diagram. That means for these independent variable values, 1, 1, 1, my memory element input functions are going to have k's in it, right? This case. These are don't cares. Why it is don't cares? Because I am saying we are never see these states. Therefore, the value of T1, T2, T3 can be either 0 or 1. So that don't care helps us to get a better minimal function. So this is if you have trivial states or non-use states, additional don't cares comes in. So don't cares comes two different sources. One source is the excitation table don't cares, or inverse definition relation don't cares. And the second source is don't cares comes in due to don't use states, as happens here. So take into consideration this one as well. Let's come to the final point here once again. So we said something about for counting x here, but we didn't say anything about what this modulo 8, which counts clock only. This is modulo 8. Where could be the what could be the practical usage of modulo 8? There are 3 of them. One of them, you could use this modulo 8 as frequency divider. How we are going to use it? You see, you need 8 clock pulses in order to see 111 here. So if you determine this staged transition, that means if you put a 3-input AND gate here, you're going to observe 1. So that means if there are 8 clock pulses passed through, you're going to pass this state, and then you determine while you are passing this state as 1. So that means you've got 8 pulses here, you've got 1 pulse here. Another 8, another pulse here. So that means these clock pulses are divided by 8. So this output signal frequency is 1/8 of this one. If the clock pulse frequency is f, then this clock pulses frequency is f divided by, so maybe this is my video, so this frequency is f divided by 8. So frequency divider. The second thing, you might consider this is a division circle. So in the division, for each 8 you got a 1 here. How many 8s are there in it is the counting of these ones, isn't it? If you put a counter here which counts this one for each 8 clock pulses here you've got 1. So how many 8 groups pass through, then you can see it here in that counter. So that is division, isn't it? What is reminder? Reminder is the value that you see at this output becomes reminder. So you've got a division circuit. So division circuit. So if you want to divide it to a different number, so you're going to design that number modulo examples. If you divide it by 7, it's going to be modulo 7. Division we said, okay. The third application could be what? Frequency division. What else could that be? There is one more I had in my mind, but I've forgotten it now. Oh, division divider. So you can use as a clock. You see the clock that you use, or watch, your watch. You can design a watch by using this modulo. So I leave it to you how you're going to design a watch by using a modulo 60 counter. So you consider on that a bit. Good question for you. So that's end of this video then.